I didn't even get to the microphone. Everybody stopped talking. So this is a good audience. So I'm going to keep my winter coat on for the rest of this so we can all be casual and comfortable. Hopefully the heat will kick on at some point, but we'll see. So first I wanted to send my regrets from Dean Ed Schlesinger that he couldn't make it. He really wanted to and was planning to up until the last minute and got called into something. So you have to settle with me. So I'm Lori Graham-Brady. I'm the Vice Dean for Faculty here in the Whiting School of Engineering. Welcome to the 2026 Don P. Giddens Inaugural Professorial Lecture Series. It's my pleasure to be here with you to honor Tamás Budavári, a professor in the Department of Applied Mathematics and Statistics, who holds a joint appointment in the departments of Neurology and Physics and Astronomy, and also a secondary appointment in the Department of Computer Science. So you have many credentials. Tamás' research centers around observational astronomy and statistics with a focus on large-scale structures, cosmology, and galaxy evolution, while his interests might lie in outer space, with applications that have contributed to the Sloan Digital Sky Survey and the Hubble Space Telescope discoveries. His work has also informed intervention strategies for vacant housing here in Baltimore. So an application for me as a civil engineer that's close to my heart. His talk tonight will highlight how challenging it is to bridge the gap between data and practical solutions in the fields of astronomy, urban planning, and neurocritical care. I don't know if I can come up with any more of a random diversity of topics, but it's impressive. Ultimately, Tamás' work strives to comprehensively understand uncertainties, and I'm sure you'll enjoy hearing about how he does that using mathematical solutions. I'd like to take a moment to recognize Don Giddens, the former dean for whom the inaugural professorial lecture series is named. He was the 5th dean of engineering at Johns Hopkins and a professor of mechanical engineering. So now it's my pleasure to introduce Fadil Santosa, the Yu Wu and Xiaomei Chen department head and professor of applied mathematics and statistics.
Thanks, Lori. So it's my pleasure to introduce Professor Alex Saleh, a true visionary who has fundamentally changed the way we look at the universe and how we handle massive amounts of data. Alex is a Bloomberg Distinguished Professor. His illustrious career is defined by his ability to bridge the gap between astrophysics and computer science. He's best known for his leadership of the Sloan Digital Sky Survey. He famously articulated the 4th paradigm of scientific exploration, which is moving beyond empirical, theoretical, and computational methods to a new era driven by massive data. Among many honors and awards, Alex is a member of the Hungarian Academy of Sciences and fellow of the American Academy of Arts and Sciences. He was a recipient of the IEEE Sidney Fernbach Award. So please join me in welcoming Alex to the podium.
Thank you very much. So Hopkins was in the early 90s. I will go in chronological order. So in the early 90s, Hopkins was really a very interesting place. So we were part of the Human Genome Project, and we were also part of the astronomy equivalent of the Human Genome Project, the Sloan Digital Sky Survey that Lori just mentioned. And it was a new kind of science, both the Human Genome Project and this, which bridged the gap between the small research grants and the billion-dollar mega projects. And it was a combination of federal funding and private funding from the Sloan Survey and, from Celera in genomics. And the other unique feature of these was that it was riding the bleeding edge of the technological revolution. So these new experiments were consisting of hundreds of unique sensors. Typically, both of those actually were built on CCDs. And we were taking lots and lots of images of the sky for many, many years. and used then advanced algorithms and a lot of computing and statistics to make sense of it. And so this was kind of the milieu that Tamás entered when he was a graduate student in Budapest. And he came out to Baltimore and spent the last few years of his graduate studies here. So nominally he graduated at Utrecht University, but he was really working here in Baltimore. And our group was in the thick of the Sloan Digital Sky Survey, and we signed up to build the database and the archive for the project, because we were working, many of us at Hopkins were working on spatial statistics, and in order to actually do the proper analysis, if the data was scattered in 100,000 little files left and right, it would have been very difficult to do the statistics, so we wanted to build a coherent system. And so Tamás came into this, and one of the first things he did is to look at the combinations of the data. So the Sloan project was very unique in that the same telescope was taking first images of the sky in 5 different colors. Instead of just one band at the time, it was simultaneously on the same night observing everything in 5 colors. And then in some other nights, we actually switched to a spectroscopic mode where we were taking of the brightest objects individual spectra. But this required much longer exposures. So while we had 500 million galaxies and 500 million stars, we only had about 1 million spectra in the end. But Tamás had the insight that when we take these 5-color exposures of a lot of the galaxies, so we had many more targets, it is actually like a 5-band spectrograph. So we are taking actually, measure the fluxes from the ultraviolet to the infrared, even though it was a very coarse resolution, but there were so many of them that one could actually try to think of a deconvolution, a unique new deconvolution, to figure out actually what is the recession velocity due to the expanding universe, what is the distance of these galaxies just by the photometric measurements, which people thought is crazy. And he invented a new statistical method, which was essentially a variant of Bayes learners. It was discovered at the same time by Friedman and Jerry Friedman and Trevor Hasty in Stanford, the same technique. So this was Tamás's entry into hardcore statistics. And this worked like a charm. But then everybody wanted to actually find the galaxies on a particular part of the sky, and we wanted to look at the spatial patterns. But the GIS systems didn't work properly. So, because the GIS systems work in projection. So Tamás actually wrote a code that was solving the GIS problem to unbelievable accuracy, so to the resolution of roughly 30 centimeters on the Earth, on the sky, but we could search in spherical polygons which were 180 degrees. So, you know, across the whole equator with this precision. And then we could use this also to find objects in a particular region of the sky or next to another object. So, shortly after Sloan, we entered another project called GALEX, an ultraviolet satellite built at Caltech, and we were a major partner in it. And Tamás wrote an algorithm which took all the 500 million stars and galaxies in GALEX and in Sloan and did a pairwise cross-match, a fuzzy spatial join between them. So that find the objects which are nearby and create a so-called bipartite partition between them. So he implemented a very clever GPU-based algorithm that he could do this in 5 minutes, that other people had algorithms that ran for days and still didn't finish. He also co-authored with Jim Gray a bunch of papers with Jim. Jim Gray was a Microsoftie who invented transaction processing and got one of the Turing Prize winners. And Tamás had a lot of papers together with Jim, and we were very often visiting him in San Francisco. Tamás's algorithm is up to this very day is at the heart of the Space Telescope data system. So it's running essentially every day, thousands of times. A little bit later, there was a contest. Tamás was already a postdoc at the time. there was a national intelligence contest. So they created, the National Intelligence Guy created a challenge problem, a hypothetical scenario that somebody walks into an emergency room somewhere in Rockville, and then signs into the logbook with his phone number. It's a New York phone number, but the last 4 digits got smudged. And then walks out after a while, but people realized that he had an infectious disease. And the people started falling in the room. And they created a data set with random phone calls and so on, and addresses and driver license numbers. So what you know, real life data looks like, which was of the order of tens of millions of records. And they wanted, so the challenge was to figure out where this person is, find this person as soon as you can. Okay, Raytheon and a couple of big aerospace companies who were involved in defense work said, okay, we need $1 million to start tackling this problem. Tamas solved this on his laptop in a weekend. Then people were amazed and couldn't believe it. And then they put a 15-person team on it and at one of the 3 letter agencies to implement Tamas's algorithm. So then they gave a big grant to Tamas that he used to tackle another problem, human-assisted machine learning. So when we have very high-dimensional data, it's very difficult to, and with a lot of random noise, but there are actually subtle patterns hidden in it. It's very difficult to detect these. And what if we actually measure, put a human in front of a screen, we start to create all sorts of random rotations and random transformations of this data, and have a human watch and put a cap with EEG sensors, the brainwave sensors on the skull, and try to figure out what the brainwaves are and use this as a feedback. Turns out that in about 20 minutes, the AI actually was driving the projections so that the pattern started to emerge. This was successful, and it led to a patent with Jacob Fogelstein. And this was partly done in collaboration with APL. Then came urban planning that Laurie already mentioned. So Baltimore has a big problem. There are 17,000 houses which are uninhabited and kind of falling apart. But the city has finite amount of money. So what to do, where to start actually the reconstruction and how to spend the money optimally. So Tamas first went and just built a GIS map of Baltimore, which had the detail of individual houses. Then figured out where are the dilapidated houses, and then define a happiness index that could be maximized with an optimization algorithm. And it turned out that the districts and areas that he recommended, that this would be the most efficient way to spend, actually the people in the Housing Commissioner's office agreed. So they thought that this is really a good idea. This was shown up in Wired magazine. And we are coming, so after Tamas got tenure, he felt that he can actually return a little bit to his roots in astronomy. And he started to work on a much more advanced deconvolution algorithm. In many ways, the photometric redshifts that I mentioned, that I started with, was a deconvolution. We had very low resolution measurements of the spectra, and using computing and clever ideas, we were able to reconstruct much higher resolution and information. And this is, I think, what Tamas's talk will be about. You can just look at his affiliation: applied mathematics, statistics, computer science, physics, astronomy, neurology. I don't have to say more. So he really represents, the multidisciplinary scientist that we should all strive to become. So it's a pleasure to introduce Tamas, who will talk about deconvolution. So,
yeah, that will be hard to follow. Well, I often joke that I took the scenic route to applied math and statistics. But when I was thinking about this talk for today, I realized I actually took a direct path from where I was towards data. So in fact, what I want today's sort of discussion about is really data and how data drives almost everything I do at this point. When I arrived to data, everything looked sort of similar, and the variety in the talk is for a reason. I want to show that data is different across disciplines, the solutions are different, and there's no one-size-fits-all solution. So if you just stop there, you would have heard most of what I have to say. All right, so let me jump in and show you some slides. And there was data. Okay, so I start from the beginning. I have some symbols here because it's math, but I want to show how direct and simple it is. And now that I look at the audience, I'm preaching to the choir. But the point is that when we see data, we start thinking about models immediately. And those models will have parameters and we'll start learning them. So an example, you walk in the tulip garden, you go to Sherwood Gardens not too far away, and you say, oh, look, the tulips all have the same height. That's a model. You might choose to parameterize it with the height itself. Okay? But you could decide that maybe the model is too simple, not enough. Maybe it has something else going on. Maybe those heights actually change with altitude. So now we have multiple models. Which one is right? How do we learn them? All that is the learning and the data science that we are into, or we are trying to tackle. Now, we are actually very lucky because conceptually, this has been solved for us hundreds of years ago. So this is the theorem or the rule of Reverend Tamás Budavári that says that we actually can not approximately, but exactly determine how we should be thinking about our model parameters, say the height of the tulip, once we have seen the data. That can be simply expressed as what we had thought about those before we had the data. And then there is some other thing here, the interesting function that we call the likelihood that connects the model and the data. Okay. There is a normalization constant that people often neglect. This marginal likelihood actually is what helps us determine which model is the best. Give some hooks for you to make comments later, or not. So anyway, with this data and this framework, of course, nothing comes easy, because even though conceptually we have a picture, the devil is in the details. In fact, applied mathematics and statistics, uncertainty quantification, numerical analysis and simulations, data science and AI are all in the details. And data is problematic. It has issues. Real data that we want to learn from, the official term in the department coined by Kerry is real data is icky. And icky data is everywhere, and icky data is different. It's icky because it has a human touch on it. There's a process that's complicated. That process is often stochastic. There's uncertainties everywhere. And it just makes it really hard to start. So that's why we actually keep on revising our models typically. We learned from the data pretty much everything, including our models. And hence the whole point of having data as the star of the show today. There's also no one-size-fits-all solution. These days, people are very happy to show silver bullets that can solve everything. I don't think that's the case. There is a lot of thoughts that go into doing pretty much everything we do in data science. So what I wanted to do today, the variety of projects, highlight 3 projects, and I will see how detailed I will get into any one of them, that have a number of things in common. They all worked on by an interdisciplinary team of scientists. They are all practical problems that people need to solve every day. They're all projects that at least one student in the group said it's impossible to do. And and they all have real data. The only difference is that the solutions end up being very different when we actually try to tackle them. So the first one is about imaging, and I mentioned this before. So when you think of astronomy imaging, you think of pretty pictures from the web. And that's arguably nothing like what the real data is like when you look at the observations. It's much more like that. For those of you who have seen analog TVs before, and mess that happens when there is no broadcast, that's how the sky looks when you look really close. And out of that ickiness emerges the pretty picture that may or may not be as pretty when you start with. Now, these are noisy and blurry pictures, and they are really hard to analyze, but we need to, because all the interesting stuff is right there in the noise. So the simple way of saying this is that most of the sources, the astronomical sources that we actually work with, are at the edge of detection. And so we just have to do it. This is actually real observations that show you real data from a telescope that is very much like the state of the art. Okay? And we are really lucky because astronomers have been very well trained to keep logs, and not just the data, but also data about data that we call metadata. So we can see here gaps and all sorts of weird artifacts that are just really hard to model. And again, this is where level 1 of impossibleness, because you would like to learn about all the sources that are within, but modeling them all properties in just one go is impossible. You could simplify away most of their properties and try to do it like that, but there's still other things in the pictures that are just not part of it. Where the moon is, how cloud the sky is, and all that thing is essentially part of the analysis. But indeed, so how do we actually learn from this, and what do we do? The usual methods either combine them in a simple, straightforward way that are either incorrect or give you very non-trivial shapes for even simple things such as a star, or they lose information, either because they only pick the best, the sharpest images, it's called lucky imaging, or because they combine data that are convolved to the lowest acceptable quality, and that gives you easy to process or easy to understand images, however, and very high signal to noise, but they are all very blurry. So the question is, could you do it better? And the answer is, it depends. We can certainly set up a forward model that does the convolution. So you could have an ideal sky behind a varying atmosphere, and that could be even a high resolution picture. And those pixels would eventually give rise to observations if you do a forward model where you feed it through a blurring process of some convolution with a point spread function or PSF, and add some noise to it. We understand the noise really well because, again, these are very well understood instruments, and the noise characteristics are tracked and understood. But still, solving the problem is hard because the data itself is losing information. So under the usual assumptions, as they say, the base rule, which we can't afford to solve, it's too expensive. We have hundreds of millions of observations, which are the data sitting right there, not in terms of the number of exposures, but the number of numbers that you might consider. And we are trying to solve for images that maybe are on 16 million or tens of millions of order. The best you can do is some sort of optimization and find the best solution that you could. The simple L2 optimization is what everybody looks at. Again, if you have seen this before, great. If you haven't, fine, we can move on. But the point is that we can write it down. It just turns out we can solve it because the optimizers that are ready to go, you can feed them in to the program and just give you nonsensical results. Part of it has to do with the fact that the results end up being infeasible. If we are looking for images of the sky that are non-negative, then it's just a constraint optimization problem that often people neglect. But that's not enough. There is also something about the solvers being too greedy. So one trick we play, a very elegant framework that exists, is this majorize, minimize idea, where instead of solving or minimizing the loss that is given to us by the Gaussian likelihood, we can actually come up with new functions at every iterate that we can show that if we make improvements on that or them, or we actually minimize them exactly, then we make improvements over original loss. And it turns out that not only we can come up with a function like that, but that function can also give us updates to our iterates that are multiplicative, which makes the process very efficient in terms of computational things, computational complexity. And not only that, but it allows us to control the convergence. So the convergence is always kept in the non-negative corner of the parameter space, which is actually tiny in comparison to entire space in high dimensions, as well as we can control how greedy we are, because we can bracket the amount of updates we are allowing in each pixel at any given time. And we can, with this approach, not only find the best possible feasible solution, but in the process, we actually find physical solutions. So the images that we get improve on the state of the art tremendously. It's almost as if we removed the atmosphere completely, almost as if we were taking pictures from a space telescope, which we aren't, of course. So that kind of improvement is hard to ignore. Not only we can do this, but we can actually go for the faint end. And on the screen, you can't see it at all, but there are faint smudges that are just really very noisy. We can actually see that. It's kind of like the spy movie when they zoom in on a car from space, and it's just a couple of pixels, but then they infinitely keep on zooming in. And if once you get to it, then you can see the car or the person. So we can do that with super resolution. We can do a lot of improvement on the view, and that latent image that we saw for is going to give us essentially deeper observations. Again, the idea here is that we want to do this for real. Now, this is hard to see once again, but the framework we developed can also give us the option of doing it in a robust way. So if there's some temporary problem with an image, such as an airplane going through, that will propagate into the solutions if you do your usual L2 optimization or the coeds, but you can actually have robust extensions or variants of this technique that get rid of it automatically. That kind of censoring or robustness is inevitable with real icky data, because there's always problems in big data sets. The big data set we have in mind, and we are pushing to sort of get this implemented, is, for example, coming from something like the Rubin Observatory, which in the next 10 years will observe observe the whole sky every 3 days, and we'll provide 1,000 observations for every part of it. In 10 years, we'll have about 100 petabytes. It's a lot of data. So when you think about inference and Bayes rule, we are thinking about doing it at scale, and that's another reason why we have to compromise. We can't always do the right thing, and hence just have to do the optimization part. Now, the project is all based on these observations that they take. So anything that we can do at the fundamental level with the images will contribute to science essentially in all key areas of the project. But that's not enough. So with this framework in hand, we actually can push for shorter exposures. Usually the normal way of doing things is that you wait until you can without sacrificing much time, but over time, the point spread function just becomes a blur. And with the blur, you actually lose information. The high frequency components are washed out. So because we can use the same framework for solving for the blur itself, we could actually, the point spread function, we can actually go for really short exposures that are maybe on the order of 10 milliseconds as opposed to tens of seconds. And those images will retain high frequency components spatially, so we have a hope of recovering better images yet. Now, this of course requires that a whole survey will be designed around this, so we are investigating this, but this is essentially, if you think about it, how a star twinkles, right? So the star, of course, has a constant light source, but the atmosphere keeps on changing, and it takes all sorts of weird shapes as long as you look at it from a very short period of time. This, of course, has been work with many people, and the team includes computer scientists and astronomers and applied mathematicians. So Yashi is a postdoc, Fausto is an undergraduate student, Yang was a master's student, graduated just last year. Andy is an astronomer at UW, and Matthias was a computer scientist, PhD student, working on this when there was no TensorFlow and PyTorch to speak of, just raw CUDA to write GPU code. The framework doesn't just apply to astronomy. So this is a project that's done in the AstroPath collaboration that is looking at the microenvironment of tumors and looking at essentially 43 hyperspectral, 43 bands of hyperspectral images to study individual cells. And in collaboration with Alex and Leo, who's an undergraduate sitting here, thank you for coming, we have been successfully applying this same inversion idea to come up with the fundamental images that give rise to these 43-band hyperspectral images. It's very early work. I will just move on from here, but just a point of the same math applies to multiple domains. Okay, urban planning. So much of it has been already mentioned, so maybe I will not talk too much about it. However, I couldn't resist. So the story goes, coming from astronomy, I was invited to give a talk at the Center for Urban Science and Progress at NYU. And when I came back from the trip, I met people at a private gathering where the trip came up. And next to me was somebody who said, don't help them, help us. And that was the then Deputy Commissioner of Housing, Michael Braverman. And we started planning projects around this. And I, of course, having lived in Baltimore, I know you live in Baltimore as well. So I don't have to tell you how great Baltimore is. But I have some pictures because I wanted to show you. So here is Baltimore. Just the time when Hopkins was funded. So we are talking 1876, and Baltimore is already a big city of 300,000 people with streetcars going and people all around. It's a true metropolis. At this time of in history, DC is maybe half the size of Baltimore. Los Angeles is maybe 5,000 people. So Baltimore is really an old historic city. And here's our Homewood campus, maybe 100 years ago. I think it's astonishing. We have an aerial photograph of it. So here's Gilman Hall, Latrobe, and Maryland. That's the original Homewood house, power plant. Just amazing that we have that picture. Now, here's an even older one from 1831. This is Baltimore from Federal Hill. Look at that. What an active and big, booming city already at that time. I think just amazing. So I couldn't resist to show my version of it 100 or 200 years later, almost 200 years later. This is, again, Baltimore from Federal Hill, and so is this one, and so is this one. And the point of all this is just again, remind you how wonderful Baltimore is. It's pretty, it has rich history that you can actually discover as you walk along the sidewalks in the city. You can see old advertisements, in this case for a factory that makes pajamas. but with all the mills around, you have heard of just a lot to uncover in Baltimore. And of course, here is our city hall where all the decisions are made. And sometimes those are hard decisions. The hard decisions because there are problems in Baltimore. Yes, surprise. Due to the fact that at its peak, we had about 1 million people, and now we have 30% less. Okay, luckily, my most recent trends are actually are improving. Now, this all happened, this discussion and my reckoning with Baltimore's past and its history, at the time when Hopkins launched the 21st Century Cities Initiative. Now, under its umbrella, we could form an interdisciplinary team that had social scientists, we had math people, we had practitioners, we had data scientists. It was, and very talented interns. It was just a very active research to start with, and this started about 10 years ago. I will not talk about the details of the project because, partly because Alex has mentioned it, but also because there's a lot to talk about. But we have essentially built on the city's existing data collection and I guess their map that they created, which could be considered today as the digital twin 1.0, a new database, an analytic database that could not only provide you with local views, but you could actually have global analytics done on the city, the entire map. So we have done, with the geospatial information about parcels and the buildings, we have done studies of how vacancy clusters, how vacancy spreads, how neighborhoods are similar to each other, how they evolve over time, how houses collapse. There was a house that fell on a gentleman. The city reached out to use our spatial database to help them identify other houses that could be at risk. And the biggest picture was really revitalization, the planning, and even finding where abandoned houses are. So when the city received funding as part of the project core to intervene, I had an opportunity to sit in the room, and when they were using our maps, these detailed maps of every building flagged with information about their history, I could sit in the back and just listen and see how the decisions are being made. And that gave rise to a math challenge and a math problem that we took on as a pilot study. So this study says, well, if I have some limited budget that has to do with a bunch of indicator variables for each house, whether something gets demolished, for example, or not. These are variables for intervention. And the house costs are very non-negative and ugly. How could we then make the math happen and start optimizing certain objectives? The simplest thing might be to maximize the number of houses that you intervene on. But it turns out to be maybe not the right solution. We tried a number of different ideas. And indeed, it's been mentioned that we actually found proxy for the quality of life. Some of them were based on anecdotes, but yet we could try them. For example, a homeowner is the happiest when the nearest vacant house is farthest. So that kind of statements can be turned into math. They can be turned into objectives that we could actually solve. The toolkit for that in our case was integer linear programming, ILP. And the funny thing was that when we were getting these results, they actually made sense. We were not sure that we would actually get good results from this, but they made sense both locally when the experts looked at it, they could make decisions locally, we could do it globally. The global solutions had the features of the local solutions they desired. But not only that, when the social scientists or the sociologists looked at our results, they also found that they made sense and they were not just efficient, but in terms of equity, they were also acceptable. So this kind of approach is certainly not a decision-making tool, but it is a information that could be used by those who actually make decisions. So one thing we are trying to think about right now is how to take this to the next step. How do we consider all sorts of interventions, all sorts of possibilities that could happen with the buildings and the houses, and build a dynamical model that can learn from the past, kind of like the equation of motion of the city. If we could have that digital twin 3.0 created, we could poke the model, and we could ask the question, if I do this, what will happen? If I do that, what will happen? And with that in hand, I can now start looking for not just one optimal solution like we did in the past, but we can think about it as optimal control. If I have 10 years of funding, how do I spend the first funding to get the best outcome at the end of the 10 years? That kind of solutions could be approachable with the data that we have, so we are hoping to take this off the ground very soon. And maybe the project saved for last that I spend most of my time on, and I am very much excited about is how do we actually use math and use data science to make an impact in neurocritical care. There is a Precision Medicine Center of Excellence downtown. The NCCU, the Neuroscience Critical Care Unit, is a very special place. I will make it very short, but what you need to know about it is this is the most expensive place you could stay. Hopkins has only 24 beds, so the resources are just very precious. And each room is like a spaceship. What do I mean by that? When you walk in, the instruments are everywhere. Data are streaming in from the patients at an incredible speed. We are talking 100 hertz measurements of all vitals. And this is a spaceship also because you literally, like as a science fiction, you literally plug in. We have data about everything that the patient does and doesn't do. Now, the pressure in the head, the intracranial pressure, is one of the most important things that we consider. This is real data. This is icky data. This is data that is so complicated that we have to do data science projects just to figure out what the metadata should have been about the data, if you see what I mean. Looking at the data at different scales will make it look very different. This is on the second scale. This is on the hour scales. Yet these are the kind of plots and these are the kind of curves that doctors look at daily to make decisions and take care of the patients. Incredibly challenging data and very interesting to work with. Now, what do we do? So with this kind of real data, the state of the art is training neural networks. Neural networks, and we call them doctors and nurses. Because I don't think we have anything that can do this except humans. They learn the foundations in textbooks, and textbooks are based on old data. But then they learn the latest and greatest things from the real data that are like the previous plots. And they need help. So at the IDS symposium was the first time when I met Jose, director of 21CC, sorry, the director of NCCU, I'm sorry. And we started talking about possible projects, and since then it's been turned into not one project, but actually many projects in parallel. So we are testing and questioning everything that there is, using the tools of data science and mathematics and statistics. Are the textbooks right? They were based on old data. After all, we have better data now. Can we say something about what the patients will do, how they recover, what are their chances, how can we help them most? The project's going many directions. We have at least 3 papers being written right now, and I cannot talk about anything. But I have some pictures that can show you that we have recent results, and they are not just pretty, but they're also very exciting in terms of what they reveal. And what that is, I can say, and I don't even know. So it's all censored for now. These are pictures that we have as of like this week. So very recent, very current things. So here is the team that does this. So here we have the leadership of NCCU, Professor Suarez, the director, and Rohan Mathur, the doctors who teach me everything that I need to know, and all the data scientists in the team. Peter is also here as our data engineer extraordinaire. If you have ever worked with medical data, you know it's really hard to get the data. He makes it happen for us. We have phenomenal help from Betsy and Vishenk as well, the collaborators who tell us about how the nurses think about things, how the doctors treat those patients. And of course, there's a whole team of applied math students and engineering students who work on this. So Josiah and Eleanor are PhD students, and the team whose figures I showed on the previous slide, just as of very recently. And Alex and Caroline are undergraduates who are just doing phenomenal work on various aspects of the projects. Again, I can't say how exciting this project is and how much progress I feel like we have made and how much more there is to learn. So, excuse me. So with that, I want to say that, here we go. I feel like Hopkins, and I've been here for quite some time. So I've been here for 25 years. I know it's the 150th anniversary of Hopkins this year. I feel like Hopkins really has been an ideal environment for me, even from the very beginning. So when I started as a postdoc in Alex's group, the freedom I had to work on astronomy, computer science, and math arguably led me to where I am right now. So I could do any of those topics. I could mix and match and think of them together to make advancements on all the projects. So we built a database to do statistics, and at the same time doing the math and the computational part as well to make it happen. It's been just a great environment for me to be here for all these years, and every time I had a chance to go somewhere else, it was better to stay, and I always did. And I really hope that this is also the environment, the same experience that our students have. It is, I certainly strive for giving the same environment where you can be independent and do your thing. And I hope that you all will think of these years that you do as a PhD students the way I think of my years when I did these studies back then, because I really enjoyed it, and I still enjoy it. Just a great way to spend your life working on fun stuff. So as for a summary, I wrote my outline, and then instead of spelling it out on a slide, I gave it to Copilot. And I told Copilot, write this as an ode to data. So here it is. So it requires some coaching. But if you were asking, if your first question is going to be, where is AI? Well, first of all, it's everywhere. And I don't even have to say it because you know it. Optimal control turns into reinforcement learning. Everywhere you can introduce it, and it's there, we can't ignore it. But so is it here. If you already read it, great. I'm going to read it anyway because why not? I might stumble because I didn't write this. I just prompted it, but see if I can do it. Excuse me. Oh, data, patient keeper of the world's faint traces, you teach us through patterns earned by doubt and care turning noise into insight and counts into meaning, reminding us that questions shape the truth we see. And in every careful glance, we leave ourselves behind. So data is beautiful, not for what it is alone, but because beauty, like understanding, is in the eye of the beholder. Thank you.
Well, thank you, Tamas. Actually, I was amazed at the complexity of the application and the math and how you brought this all down to somebody like me being able to understand it. So it was a very accessible talk, and congratulations. And we have a small memento of the day for you. So I think we need you to come over for the photo.
And hold on to it like this?
Yeah.
Thank you.
It will smile.
Thank you very much.
Thank you very much.
Thank you. What did I get?
We have some refreshments in the back, and I think there's plenty of fuel for conversation here. So, yes, Dan, did you have a question?
If you guys have any questions, I mean, we have.
I just want to say that Tamas, something that didn't get mentioned was that Tamas is also a recording star. So we'll just leave it at that.
The secret is out now. Thank you very much.